Hello and welcome back to another installment of Ebatco Lab video. In this video we will take a look at some interesting behaviors of non-Newtonian fluids using the Viscometer in our nano-analytical lab. Fluids can be characterized in different ways depending on its physical properties and how we model it in fluid mechanics. Fluids can be first characterized into one of two categories, Newtonian or non-Newtonian. Newtonian fluids are ones where the stress is directly proportional to the rate of strain. While no fluid is truly Newtonian in all conditions, many common liquids and gases can be modeled as and assumed to be Newtonian under most ordinary conditions. Water, for example, is Newtonian under most normal conditions. Everything else is considered non-Newtonian. Non-Newtonian fluids have nonlinear relationships between the stress and the shear rate or shear rate history. That is, they can be either time-dependent or time-independent. From there, non-Newtonian fluids can be further subcategorized depending on how the stress and the rate of strain are related. To demonstrate some of these relationships, we've prepared samples of a couple of common non-Newtonian fluids to test using our viscometer. The viscometer uses a calibrated spiral spring to measure the torque required to rotate a spindle of known size which is immersed in the sample. Using the measured torque and the size of the spindle, it automatically calculates the viscosity. From there, the software can calculate the shear stress and the shear rate by the measured rotational rate, the size of the vessel housing the sample, and a few other factors. For baseline, let's take a look at the behavior of silicone oil with the known viscosity. Placing the liquid in our system and running a program that ramps the shear rate over time, we can measure the shear strain for analysis. We see that if we graph the shear stress against the shear rate, the data follows a linear trend. We expect to see this from a Newtonian fluid. We also see that viscosity increases linearly with increased shear rate, another clear indicator of a Newtonian fluid. Now let's take a look at how ketchup behaves. You may not know, but ketchup is a great example of a non-Newtonian fluid. Ketchup is a fluid that undergoes shear thinning. It is known as a pseudoplastic. For example, when you have ketchup trapped inside of a glass bottle, hitting the bottom of the bottle gets the ketchup to flow. This is because that when the ketchup is subjected to force, the viscosity drops, enabling the ketchup to flow freely out of the bottle. Looking at the viscosity as a function of shear rate for our ketchup, we can see that it decays as we'd expect for such a material. Looking at the shear stress, we see that it increases, but it increases non-linearly with increased shear rate. This exhibits the shear thinning properties that we expect out of the ketchup, which is a good thing, otherwise we would never be able to get it out of that bottle. Shear thinning fluids aren't the only non-Newtonian fluids we run into. Some fluids undergo shear thickening, known as Dilantin fluids. When these are exposed to shear forces, the fluids experience an increase in viscosity. An example that I'm sure you've all seen is a cornstarch water mixture. In this concoction, the shear thickening phenomena is so extreme that so long as it is undisturbed, it's a liquid, but when force is applied, it thickens to the point where it is possible to run across a pool filled with the mixture. If we look at a plot of viscosity as a function of shear rate of this mixture, we can see that it increases as we'd expect. Furthermore, if we take a look at the shear stress as a function of shear rate, we can see that it increases non-linearly. These indicate that our mixture is indeed non-Newtonian. The examples of shear thinning and shear thickening materials that we just discussed were time independent, but there can be fluids that undergo time-dependent shear thickening or thinning as well. A time-dependent shear thinning material is referred to as Thixotropic, and a time-dependent shear thickening substance is referred to as rheopectic. True rheopectic fluids are rare. They undergo further thickening with sustained force. Under constant shear rate, the viscosity will increase over time. Some examples of fluids with these principles are certain lubricants, gypsum paste, and certain printer inks. Thixotropic materials are slightly more common, but still more rare than similar time-independent pseudoplastic materials. These materials will continue to become thinner as force is applied over time, and take some time to return to their more viscous state, unlike time-independent fluids which will thin nearly instantaneously with increased shear rate and then return to their thicker state as soon as the force is removed. The viscosity of a thixotropic fluid will decrease as a constant shear rate is applied over time. Drilling muds are an example of this, as are certain types of clay. Well, that's all for this installment of Ebatco Lab TV. We hope you enjoyed and will visit us again. Keep an eye out for more videos covering diverse topics from our lab. If you have any questions about either the methods or the instrument you saw here today, please don't hesitate to give us a call or shoot us an email. Our contact info can be found on our website. And as always, if you're interested in nanomechanical and surface characterization lab services or consultation, please give us a call. We'd love to hear from you.